So this is second lecture on risk conscious operation management of complex engineering system. In previous slide I have explained you what is complex engineering system, what is the role of safety risk, and why the word conscious has come, because human is a conscious entity and they have role in design, right from concept, design, operation, maintenance, aging management, and going to the greenfield level actually. So humans are a common link, and that's why risk conscious operations management. And now this subject has been built, or rather it is fundamentals of reliability, and that at component level and safety level they form part of dependability engineering. So week 2 has been dedicated to dependability engineering, and herein the reliability has been discussed in the context of at the component level as well as at the system level. So system level, some aspects like for standby system, that will be discussed in lecture number 3, while here we will see that rather typical parallel system, series system and component reliability. What we understand by reliability? In simple words, reliability is a probability of failure free operation of a component or a system or a service for a up to a given period of time and under stated conditions. So having spelled out the definition of reliability, then we will look for what is its mathematical formulation. So that means a mission time is a very critical component of reliability. So that means reliability should be discussed as a function of time. So we can see here on this slide, reliability as a function of time, that is RT, is nothing but probability, okay, and capital T is a random variable, and small t is the real time the data that we obtained, and then C1, C2, C3, they are the conditions, because any component when it operates, the condition under which it is operating impact the operation time of that component. If it is a harsh environment, let us say if the humidity or temperatures are very high in the area, then component will operate. Let us say take the case of electronics. So if the temperatures are not maintained to ground Bayesian condition and it is seeing the harsh environment in that respect, or humidity is high, it will not meet its intended mission time. So given conditions are very quality of the component, if the component is not having quality or is not meeting the quality marks, so then also component will not perform. People who are operating that system, that also matters. So like I would say, reliability is a function of time, and it is equal to probability of component operating at least up to its or more than its mission time t, and the conditions are it should have quality, it should have trained manpower, it should have environmental condition for which it has been designed, then only I can talk about the reliability. Probably this concept of reliability as a function of time is clear, and even though there are many distributions that we discuss in reliability engineering or in statistics, but here we will essentially be discussing the exponential distribution. Why? Because it is extensively used, and through this distribution we will try to exponential distribution means constant failure rate. Any component when you put into service, it might have initially more failure because of learning rate or because of quality related issues and all, but then later on the failure rate come down, and then the component operates for its lifetime with random failures only, and then which makes the failure rate to be constant, and then the failure again start building up or increases when the component becomes old or aged. So that is how we get so constant failure rate. So we are having all the solutions here in terms of our constant failure rate. Now let us say how a mathematics of reliability works. Now, when we are talking about the failure, let us say a component has a failure rate. Failure rate is typically or customarily defined in reliability engineering by lambda. So we can see here we have lambda as a failure rate of 5 into 10⁻⁵ per hour. Now you will ask me where from this failure rate has come. This failure rate has come based on the past data. That same component or similar component has been operating in many places, and then we found out how many failures it has experienced and how much was the total accumulated time. Failure rate divided by accumulated time will give us the failure rate. So here we have failure rate 5 into 10⁻⁵ per hour, and these type of data, they are available in many databases that are available in open domain, like IAEA TechDoc, International Atomic Energy Agency TechDoc 478 gives failure rate for many components, pump, heat exchanger, electronic boards, and like that, wall, pipes, everything. So these are the databases. They have compilation of data, and probably when we built our plant, you can use the generic data, but as we fine tune the our exercise, then we should try to have real data that we want to use it. Maybe for even design also of a plant, we use generic data. Because we don't have any other option, we can use from similar plants. But then as the time passes, it should be our effort to come to the plant specific data. So let us say how we have done. So mission time is T is given here is 7 days, that is 168 hours. Failure rate was this. So equation, reliability equation for considering the exponential distribution is exponential minus lambda T. Lambda is failure rate and T is mission time. If you multiply these two, we get reliability is the probability is around 0.992. That means sometimes people talk about percentage also. 99.2% is the reliability, but that is not correct. Reliability should be talked in terms of probability only, which is 0.992. So this kind of thing, it helps us in giving a confidence on what a component is going to, how is component going to serve us, and it's a big deal actually, now we have to understand, that was a simple calculation that we did. Now we have to understand the axioms of reliability. Means what it means is better understanding through this matrix. So RT, if reliability is 1, only at time t is equal to 0. Because once the component start operating and the time element comes into the picture, the reliability start going down. Okay. Now why it goes down? Because it is a dropping or reducing function. Okay. As the time increases, reliability goes down in exponential, whether it is exponential model or any other model. And our reliability at time t is equal to 0. Okay, at the reliability is 0 when time is infinity. Okay, so we will read it. Reliability is a function of time, that means infinite time will be 0, because the component will fail. Anything which is built will fail actually, So what we understand from here is reliability varies from 0 to 1. So these two axioms has led us to this understanding. Reliability varies from 0 to 1. And then from here we get a very important insight, that reliability, either the component will operate or it will fail. And these are the two possibilities we assume. Then RT reliability plus failure probability is equal to 1. Either it will be in this state or this state. So here we are considering only two discrete states, that is operating or failure, and that is total sum is 1. Now since we got the reliability for an assumed component in the previous slide, 0.992 was there. So 1 minus 2 is failure probability, and the failure probability comes to 8 into 10⁻⁻³ 3. So, when we estimated the reliability, we got the failure probability. Now, this failure probability is a very important parameter, because in real life situation, when we have the failure probability of the component, it helps us in prioritizing the inventory in the plant. It helps us in maintenance management. That means the component for which the failure probability is higher should be resource should be dedicated more. For a component for which the probability of failure is less, we can save some resources from less failure to more failure, and that way we can optimize our plant maintenance activities. Okay. Now, this was for what we discussed was operational reliability. Now, there is another notion of reliability which is in design domain, and we know that designs are nothing but stresses that is anticipated for a component in the design and strength that is available. So, here, but the difference here is those stress, strength, the whatever we used to postulate, we used to have the point estimate, but the science of data has evolved, and the statistics has helped us, and now what we have is we are able to characterize uncertainty associated with the stress and uncertainty associated with the strength. This is a normally distributed and around the mean value of stress and mean value of strength. What this particular model is good for design or inherent reliability. If the component is designed, then based on what kind of resilience or strength, that is stress and strength, they play out together for ensuring the life of the component meeting its function. So, it is called design reliability or inherent reliability. Okay. And that is where what made it possible. This thing was possible because years of operation on materials and design. Now we are able to characterize uncertainty. That means what will be the mean stresses and how the stresses are going to increase, or what is the one time stress that will come, the event that will put the system to maximum stress. In plant itself there are variation, like suppose if a plant is their temperature varies by 20 degrees centigrade. So, these two things if we take into account, or if we see if a plant is in open space, then it will see all weather conditions. So, it is not that it is facing the same environment. So, that leads to corrosion, kind of degradation and all. Our operational stresses also, they make these systems and all, like internal shocks and all that, and that is where the strength. Now, strength also is a random variable. Why? Because what we estimate and what material we have, there will be definitely some variability in material property, material characterization, and those things should be captured for capturing the uncertainty associated with the behavior of the material in real time domain. For in the absence of this, we were using the factor of safety. If something the process design pressure, if we assume 10 kg, we'll assume by a factor of 1.2 12 kg, and then strength also similar way we used to interpret, and we used to ensure safety. But then now there is a very elegant mechanism to characterize uncertainty. So, what is the outcome? Outcome here is that we are able to build by optimizing stress, strength and design the system. So, sometimes overburdened system also, they used to lead to increase in risk and unreliability. That component can be reduced. And with this thing, we have talked about the fundamentals. Now, when we talk about the system, so far what we discussed was at component level. Now, when we have a parallel configuration, reliability configuration, series configuration, more complex configurations are there. How to go about assessing? Let's say example of a electronic board. Electronic board have laid out component on this, and mostly the reliability estimate or the failure estimate of the board is obtained by summing up the reliability. That means what is assumed is that If one component fails, then the board operation is adversely affected. It will not perform its intended function, and that is to some extent true also. So, that is where we use series system modeling, series system configuration that we use. And in series system, so first of all, let us talk what is the reliability block diagram. This is a very fundamental and very primitive technique for modeling the reliability, where complexities are not much. Let's say I can talk to about electronic board developed around the semiconductor logic or relay based logic. But the moment we talk about the digital logic, then hardware components is okay, but software component creates complexity. So let us remain in the domain where we can talk about series. We can explain the series system and final system. So first characteristic of reliability block diagram is it has got one input and one output arrow. That means input function and output function, and then the blocks will be represent component. So the components are connected in series, and how it is connected, the output of one goes to the input of other, input of two, output of 2 will go to, so like that they connected, and finally the output is delivered. In many industrial domain we see them assembly line, they work back to back. If there is one problem in one component, then the whole assembly line gets affected, unless until redundancy is there. So wherever we want redundancy, we will put some component in parallel. Let us say a component 2 is giving more failure problem, then we will connect alternate, so that we can our operation can go with a small intervention and all that. So this is called series reliability block diagram for series configuration. Now, how we treat this thing in actual this thing. So now let us say we are going for reliability modeling of a series system, and to begin with, let us understand a assembly line, simple assembly line where redundancy is not there. So one component is back to back, second, third, fourth, and all they are connected. So let us assume. So if we characterize RS, system reliability by RS term is a function of time, and then for individual component we say RIT, that means component ith component, so reliability. So since they are connected in series, so system reliability will be nothing but for giving the output, component 1 also should function in reliable manner, and component 2 should also function in reliable manner, component 3 also, then only we can have a complete system reliability. If any component fail, then there is an interruption, so that means the system does not work. And if you have to write a mathematical equation, since it is n, so we have multiplication. So system reliability is nothing but R1 into R2 into, that is reliability of component 1 into reliability of component 2 into reliability component and reliability of component 4. If I multiply this, it is nothing but RS system reliability is equal to I is equal to 1 to 4, because we have taken a case of 4 components. So I is equal to 1 to 4 and RTI. So individual component reliability, this is a multiplication sign. Okay. So and now what happens is, in exponential distribution, if we have the exponential lambda terms get added up. Okay. So like if I multiply, if I put e raised to power lambda 1 t into e raised to power into lambda t 2 t. So t is common, but lambda is different, let us say. So then all the lambda will get added up here. So we have seen all lambda I component added up, and t remains same because mission is same. So system reliability is nothing but, for series system, it is exponential minus summation of all the failure rates, ith failure, 4 failures, and multiplied by t. So this is the reliability equation for a series system that we have. Now let us see some practical example. Okay, we have a pumping system. Okay, now in this pumping system, this is a tank at lower elevation, and this is a tank at higher elevation. It happens in all our household buildings and all that. So suction is taken from here. There is a filter, and there is a valve, and then pump and valve V2. So two valves, one pump and one filter. And of course these two tanks, they create a system. But suppose if you wanted to, because tank should not be considered, they are passive component. their failure is very rare actually. We assume that. Then what we require, if I have to do a reliability analysis, what I do is, this is a system boundary. In any reliability analysis, we have to create a system boundary. What we are trying to analyze, we should know, and their connection with the input and output should also be known. So here we know that what it matters on the reliability term is these components: filter, F means filter, then valve V1, P and pump, and V2, and that is a discharge valve, and we have a system here. So we have built this system. So we are trying to understand some reliability principle of reliability block diagram also. The component inside the boundary will form the system. So this is our system. Then identify the input and output connection. So here we will have input, water is coming here and it is going out. So this is input output. RBD have one input and one output. Okay. The system reliability block diagram of the system, whatever we are giving here, we have here, that is filter, valve, pump and V2. Normally in reliability block diagram, the placement of the component in itself can give you some idea how they are connected, but this doesn't happen all the time. We will discuss this point also. So we have output. Now what I have to do, reliability of all the component, that means for meeting the mission, that is successfully, pump take the suction from the underground tank T1 to overhead tank T2, the filter should work, valve should work. So filter should be reliable, valve should be reliable, pump reliable, and so we formulate the equation here. Okay. So we have failure, assume that we have component failure database. As I told you, either you take from generic sources or anywhere you can make it. So filter, we have the failure mode is choking, the filter. So these all these things, they form part of the reliability engineering. So its failure mode is choking. Then its failure rate, let us see, we got from the database 2 to minus 5. So reliability will be 0.998 actually. And then suction valve, discharge valve, it was assumed both have same failure rate because they are valve, similar components. Pump failure rate and all, we have this thing, and all this data comes here. System failure rate will be addition of all the failure rates, you know. So as system failure rate is summation of I is equal to 1 to n, 4 component I is to 1 to 4 and lambda I. So like if we adapt, so 1.12 is the failure rate of the system. And once we have the system failure rate, it is simple to calculate the reliability of the system. So 83.5% it will work for 150 hours. We have chosen a mission time of 150 hours. So we make a guess from here. The system is not all that reliable, and then we also know which are the contributing factor. The maximum, the lowest failure rates were for filter because it is a passive component, and then pump is 3 into 10 to the minus 4, 5 into 10 to the minus 4. So that means the pump is contributing maximum. Okay. So if we are not satisfied with this, what we will do is we will provide a pump in series with this existing pump. So that will increase the, so pump was contributing maximum to unreliability. So we will have one more pump here. So you see how systematically we got the idea for doing a modification into the system. Everything is not all that simple, but then in principle we came to know how to understand the system and how to prioritize our actions by using the mathematical calculations. So this is just one illustration was there. Now let us go to other configuration, and the other second configuration is parallel system. As I told you, you put one more pump in the parallel to the other pump, will have higher reliability, because if one pump fail, other one will be there. So similar, so then that means we can have a parallel system. So one pump, second pump, third pump, and if you want to increase the reliability of the system. We will understand even how the common cause can have a consequence, but then for time being, this is the input, let us say, and this is the output. and that when higher reliabilities are required, we use a pump. Let us say if you have to achieve 0.9999, single pump will not be able to deliver. For that, we have to use parallel configuration. Okay, so this is the configuration we have, and then we are trying to build the model for the formula for parallel system configuration. So what happens is, failure probability of 1, 2, 3, 4, and if it is 1 minus, it will give me the reliability. Okay, we have seen RT plus FT is equal to 1. So the RP reliability and this term goes here. So reliability is equal to 1. So we have got reliability 1 minus FT, this term. So and product of this, because in parallel system, unless until the last component fail, the system doesn't fail. So it has to be failure of 1, failure of 2, failure of 3 and failure of nth component, then only parallel system fails. This is how it works. Now here we can go next step, reliability of the pump system, RP is reliability of pumping system, is equal to 1 minus as it is, and then again since we know the reliability, so 1 minus RT, failure probability can be replaced by 1 minus RT, 1 minus RT2T, 1 minus RT3 and RNT. So our generic formula we are able to evolve 1 minus multiplication of 1 minus RT of ith component which form the system. It is so simple actually, and this thing can be used in our practical life when we want to understand the system, its performance, and we want to improve the performance of the system. So this is what we discussed about the parallel system. But yeah, now if I take the example the way we discuss on reliability of series system, even so, let us say there were two pumps. Okay, they are connected in parallel. Here I will bring in a common concept of, because if I use this method, I will get a very optimistic results. I will tell you why. There are two pumps and we know that there are failure rates 5 × 10⁻⁴, and the mission time is 100 hours, two pumps, and then reliability will be, we know that once we have failure rate 0.950. Now if we estimate the reliability using the same formula, 1 minus RIT, and then so that means this becomes a square term, and already we have 0.94 for each pump, so we get a 99.75. okay, for reliability of one pump we were getting 950, we have improved 99.75. okay. So what insight we got? This shows that when two pumps are connected in parallel, the reliability increases, as can be seen in the system. The reliability of one pump is 0.950, while the reliability of two pumps is 0.9975. But the point here is, we are telling that these pumps are there. Let us say these two pumps, they draw power from the same source. That means if power goes, these two pumps will fail. Okay, or the oil which was made up into the system, the pump was pump will, if the oil is not good, they will also fail. They will not be able to meet the mission. If a maintenance person was working on that, he did the same mistake on both the pumps. This effect is called common cause failure. Or suppose a flood, these pumps are located in some area and the area floods, both the pump will fail. So that means what estimate we got here is a very optimistic estimate. We have to consider common cause failure which can fail both the pumps. Okay, so unless until we take into account the impact of common cause failure, we will be giving, please note, most of the books they give two parallel system, two component, and the reliability you estimate. No, that is not the way. Unless until you factor in the common cause failure, and you will see the impact also. Now after considering the common, and what is common cause failure? Common cause failure is nothing but reasons or causes or locations which lead to, so one cause which leads to more components, or components which are operating in parallel, or components which are having a standby redundancy. We will see what is standby, but one cause impacting adversely the parallel system configuration. Okay. So, earlier what we talked about is independent failure of pump 1, independent failure of what 10 to the minus whatever figure was there, we consider 10 to the minus 4 that was there. So, common cause will be 0.1. It will not be all that frequent, but it is less than the independent failure, but it impacts the whole configuration in adverse manner, because you cannot use simple parallel redundancy principle. So, if it is 0.1% of independent failure, 5 into 10 to the minus 4, it will become 5 into 10 to the power 5. So, now with this, if I do the calculation, and you can see for yourself, common cause factor comes 0.995, okay, and then we have measure inside is, it is the modified 2 pump system reliability becomes 0.9975 into 0.995, that means 0.9925, which is less due to common cause failure. So, it is dampening the independent failure probability, and it is very crucial if we analyze a system, and probably all my students, they will use this principle to factor in the common cause failure, instead of going from whatever ready-made examples are available in the book, and learn from about common cause failure in many. There is a beta factor model, MGL model, alpha factor model. All those things probably, if required, will come to that. Otherwise, you can explore in the books, and they are there actually. And it is very important to understand the common cause failure. There, human factor is also one of the common cause. Okay. So, now overview of this is like we have seen series parallel system reliability definition we have understood, and modeling has to continue in the next lecture also. So, now in next lecture we will be seeing the first component of that is dependability matrix, that is reliability. Then later on we will take availability, maintainability also, and of course in little because in the first lecture itself we have taken reliability and all, so risk and all. So, we will be sort of for the sake of continuity we will be repeating risk also in this lecture.